Just continuing. All right. So for part 1, express 8 cos theta minus 15 sine theta in the form that they've given, uh, where r is positive and alpha is acute, stating the exact value of r, and they need you to give this to 2 decimal places of alpha. Normally, calculations that or answers that you give in degrees are given to 1 decimal place. However, here they have explicitly mentioned that they want 2 decimal places, so we'll just follow. Now, the simplest way to do this is just to remember the formulas for these two. So with r, you take the coefficient of both. So you take the coefficient of cos, which is 8, you square that, you add that to the coefficient of sine, and you just take root. What's giving you what? It's giving you 17. And they wanted the exact value of r, which is basically, if this is, what was this coming to? Just a sec. Yeah. So if this was root 289, they just don't want you to leave it at this. Go to the exact value. Normally, when they mention exact values, they normally mean that they don't want decimal values. They prefer you give it in terms of pi or in terms of a fraction, so that you get the full value, the exact value if you take that. In this particular case, they just wanted you to give your value as 17 rather than leave it in between, which surprisingly rhymed. Okay, for alpha, you have tan inverse, you have 15 over 8. Don't put the minus sign there because you want it to be acute, which I think almost always you want it to be acute. So you, even though this is minus 15, just take it as 15, and you get what? 61.93 degrees. Your answer isn't over yet, though. You have to put it in the format that they want you to put it. So cos theta plus 61.93, and there you go. Hence, solve the equation 8 cos 2x, and so on. So basically what they've done here, this is really your answer to the previous part. In fact, it's not quite your answer, because here they have 2x. Here you just had like x, or theta rather. So if I write this as 17 cos 2x plus 61.93, this would then be equals to, as we saw here, instead of 8 cos theta, it would be equals to 8 cos 2x minus 15. Instead of sine theta, it will be sine 2x, right? This is what's given in your next question. Hence, you can substitute it with this expression. That's the idea. So what the question is really about, what the question really is saying, it's saying you have 17 cos 2x plus 61.93, and this is equals to 4, and solve for x. That's what actually the question is saying. Now, what do you do in these cases? Now, the first thing, before you do anything else, you should adjust the range of values of x. This is for x. What are you given? You're given 2x plus, whoops, yeah, so you are given 2x plus 61.93. So for both these values, what you do is you first multiply into 2. I mean, if this is like, this is some value of x that it is below, right? So you first multiply it into 2, then you add 61.93. So you get 61.93. So this is supposed to be greater than 61.93. However, it is less than 180 into 2 should give you 360 plus 61.93. Okay, so this is 421.93, right? So this is your effective range of values for 2x plus 61.93 that you calculated from the given, why is this happening, from the given values of x. Okay, now you want to solving your equation. So you can write this as cos 2x plus 61.93 is equals to 4 upon 17, and hence alpha, which is your basic angle, would be cos inverse 4 upon 17. And remember, in this case, your alpha would then correspond to 2x plus 61.93. Anyhow, what is your alpha coming out to be? Yes, your alpha is coming out to be 76.4 degrees. Let me just keep this to let me just write this properly. 4 degrees. This is your value for alpha. Now let's draw your quadrants. So these are your quadrants. Why is this such a bad color? Okay, so add sugar to coffee. The way I like to remember it. This is positive 4 upon 17. So cos is only positive in the first and the third and the fourth quadrant. And again, here you look at your effective range of values, because your alpha is corresponding to 2x plus 61.93. Hence, you don't look at the range that was given for x, you look at the range that we calculated for 2x plus 61.93. And as per that range, both these quadrants should fall within it. Here, your alpha is going to be equals to 2x plus 61.93. And it is fine because 76.4 is greater than the lower limit, that is 61.93, so we're good. In the over here, your alpha doesn't necessarily correspond to whatever you have here, like in terms of theta, right? You first have to do 360 minus alpha, and that corresponds to whatever value you have, which in this case is so forth. You might, in fact, since the upper limit is like 421, which is like greater than 360 degrees, it's literally rotating and coming out to be somewhere along this area, this particular point. But if you look at it, it still won't be enough for us to take a third value. Why? Because even if we take, because in the first quadrant, alpha is simply what we're interested in, so 76.4. Even if you add 360 degrees to this, if you add 360 degrees to this, that gives you 436.4, which is greater than the value you have here. So you're not going to be rotating another round and getting another value in this particular case. So in fact, in this question, there are well, for 4 marks at least, quite a lot of things that you have to take into account. Anyhow, so you will only have 2 values of x then, and let's write them down. So 2x plus 61.93 is alpha, which was, what was alpha? 76.4. And hopefully you'll use the exact value of alpha. You'll have it in your calculator rather than just using a rounded off version. Because if you round off at every step, then you're just going to get your answer would just deviate from the answer in the marking scheme, which isn't too good, right? So these are the 2 values you're getting. Then what do? You take this to these 2 values. You take this to the other side of the equals to sign. So you subtract 61.93 and then you divide by 2 to get your value of x. And what is that value? And again, for that value of x, you will then round it off to to sorry, not to two, to not two significant figures, but to one decimal place, because that is the rule in angles in degrees. So yeah, you get this. Okay, so the curve with the equation, and they have given you the equation where a is a positive constant, has only one point in the interval 0 to pi upon 2, at which the tangent is parallel to the x-axis. Okay, so if the tangent is parallel to the x-axis, if you visualize this a bit, this is the x-axis. It is perfectly horizontal. Perfectly horizontal lines have a gradient of 0, and if the tangent is parallel to the x-axis, it also has the same gradient, which is 0. Find the value of a and state the exact value of the x coordinate at this point. Okay, so you need, you can make use of the fact that that at whatever point that they're talking about in this particular interval, if you draw a tangent at that particular point, it would be parallel to the x-axis. That is the point. The gradient of the curve or of the tangent is the same thing. At that particular point is 0. This is the same thing. So that is something that you can use to your advantage, because then you know that dy over dx, which is really your gradient, should be equal to 0 at that particular point, and from that you can find x, right? So however, the issue here is that you would have to use product rule, because there are two separate functions multiplying. So your u should be e power ax, u prime would be e power minus ax into minus a is equals to, so it's minus a e power minus ax. That's what you get, right? Your v is, what's your v? It's tan x. V prime, I believe, is sec square x. It's given in your MF9, so like you really don't need to worry about that. And that's what I like to do. I like to write down u and v and their differentials beforehand. It just makes life easier and reduces the chance that I'll make a silly mistake later on. Okay, so then the differential is equals to u prime v plus v prime u. And you just input. What was u prime? It was minus a e minus a x. V was tan x plus v prime u. Although you can't really see because my handwriting is so bad, but it's u prime v plus v prime u. Okay, what is v prime? V prime is sec square x, and what is u? U is e minus a x. Right, and this has to be equals to 0. That's the important bit here. Now to do so, 0, you need to do a little bit of simplification. So I can take e minus ax as common, which gives me minus a tan x plus sec square x, right? So what you basically done is हमने इसको लिया, you took this and you took that as common. Now what you get, then you can split this, so you get e power minus ax is equals to 0, which really doesn't help you much, because as you should know, an exponential is not, well, it's difficult to imagine a value of x that would make the exponential go to 0. So it's like this exponential will look like something of along this, these lines. It would look like something like this. Yeah, and it would really wouldn't touch your x-axis, which is where it would be equal to 0. So yeah, well, this doesn't really help us. But the other thing might help us, which is minus a tan x plus sec square x is equals to 0. So you have, um, let's say, sec square x is equals to a tan x. Sec square x is basically 1 upon cos square x is equal to a tan x, right? Uh, or is there a better way we can simplify? Because like what we need to do now, if I just go back to the question, you need to find the value of a, okay, and state the exact value of the x coordinate at this particular point. So we just need to solve at this point to, wait, we need to solve. We have the equation. We have the fact that a is a positive constant, and it has only one point in the interval of this at which the tangent is parallel to the x-axis. Sahi, sahi. Okay, so in this particular case, a is 1 upon, let's say, tan x cos square x, right? Well, this doesn't seem too good. Perhaps an alternative approach might work. Well, what if we take sec square x and we convert that into tan? I believe there's a property for that. Well, your MF9 should be given there. So like, I'm very bad with remembering stuff. Yeah, so 1 plus tan square theta is equals to sec square theta. Okay, so we can use that, because are we given sec square theta? Yeah, we are. So sec square theta is 1 plus tan square x in this case, because it's sec square x, and this is equals to a tan x. So you just cross this out. I think this should give us a better chance. Okay, so then you have, what do you have? You have tan square x minus a tan x plus 1 is equals to 0, right? Now that you get a quadratic equation, you can actually solve this. It'll be a little difficult to solve with the a stuck there in between, though, being very annoying. But you can still put it into the quadratic formula. So like, so tan x is equals to plus a plus minus root a square minus 4. It's just 1 into 1, and this is going to be 2. So you can pop it like that, and you can solve it from there to give you values of tan x in terms of a. And how can we do so? Let's just look at it. We're running out okay, we have space on the other. Okay, they've given us a lot of space. Very nice of them. Uh, Otherwise, it's just so annoying when you're doing the paper and then you have to continue on a blank page, and at times you don't even give the blank page. It's very sad. So you have plus minus. Now if you really just look at this, this is like a square minus 4, and we need, and you have an overall root here. We could do the a square minus 2 square property. Yeah, we could do that. But then it's on 2 as well. Okay, so let's look at this. All right, so my apologies, we were slightly on the wrong track here, because if you guys continue solving, you'll just get 2 roots in terms of a for tan x, which really isn't going to help you. But the mistake that we were making is that we didn't read the question carefully, and you have to say that it has only one point in the interval, which is in basically your first quadrant. So like, And first quadrant, all the trigonometric functions are positive, right? So you got to look at this and figure out from this what value of a, so like what value of a gives only one root. That's the idea. So like basically gives only one value of tan x, because if you only get one value of tan x, then you're only going to get one root in that particular range of 0 to 90 degrees, right? So to figure that out, like if the idea here is, since this is like, if I can just rewrite, a upon 2 plus minus a square minus 4 upon 2. So as long as there's some value coming from here, there will always be something added to this, something subtracted from this, giving you two values. You only want one though, so it means this has to be equal to 0. And for that to happen, it's very simple. You just put a is equals to 2. You can just simply you could equate that properly, but you could just read it off like, if a square minus 4 here, so like if a is 2, 2 square 4, 4 minus 4 0, and hence now this turns out to be 0, which leaves, if you think about it, tan x to be a upon 2 plus minus 0. And because plus minus 0 can really be just excluded, and that is how you ensure that you'll only have one root of tan x. You don't have one value of tan x, and hence you'll only have one root of x in the first quadrant. So you can just simply pop this in now, since you know that a is 2. So tan x is equals to 1, and then you just simply solve for x, right? So tan x, the x is basically tan inverse x, oh sorry, tan inverse 1. Why is that? Because we're just interested in this happening for the first quadrant, and in the first quadrant your basic angle is the same as your value of x basically. So x is, again, I believe we were in radians. The question was in radians, so we just give it in radians. X is pi upon 4.